Welcome everyone to Gems from the Wisdom Traditions, a conversation circle sponsored by Still the Moving Center each Saturday afternoon or evening, depending on where you might be. We're happy to have you from wherever you might be tuning in. Cliff and I are in California right now, in Northern California. Saying hello to you in less than warm Hawaiian weather. This idea of the dark caverns of the brain beginning to glow luminous is something I think we might have just a glimmer of today while we are able to listen to Janani Lakshmanan. And Janani is someone who has graced us with two different talks in the past, both of them on Bharatanatyam, which is something through which I met her. She has performed Bharatanatyam, as have her students at our Diwali performances and many others as well. But there's another side of Janani that some of us haven't gotten to know as well, and that's the fact that she is studying for her PhD in math at Manoa. And so she's going to bring some of her expertise and knowledge along those lines to our consideration of sacred human geometry. And she's going to bring it to us from the classical tradition of geometry, the more mathematical, perhaps Euclidean, I'm not sure, geometry, and probably hearkening back to the Platonic solids, which in turn harken back to teachings from Pythagoras, who brought them from India, where Janani's heritage hails from. So through a long string of cultures, we're coming to today with Janani speaking to us on sacred human geometry. So Janani, we'll let you take it away.
Thank you so much, Renee, for that wonderful, sweet introduction. I'm going to request to share so I can put my little PowerPoint on the screen. I do appreciate you all tuning in on this wonderful weekend of gratitude and celebration. And I also appreciate you all, especially Renee, being willing to trust me to talk math today. So just if I can get a general sense, how happy are we with our mathematical abilities? How many of us would we say love math, or yeah, I could do this for my entire life, which is where I am today? No. Okay, okay. I got one thumbs up, and I love that person, whomever that is. So thank you.
I love math too.
There you go. I got two thumbs ups. That's awesome. If you don't love math, if you're not the kind of person that could see themselves doing it for their whole life, that's okay too, because that's who I'm hoping to address. I think the sort of resetting of our consciousness, of our perspectives on these things, is probably the most meaningful part of the quote that Mary read earlier today. And so I think that maybe I'll be able to share a perspective that might assist us in doing that. So I will go ahead and share my screen. And go ahead and start my slideshow. So as Renee mentioned, I will be sharing on the classical geometry tradition, sometimes known as the Euclidean geometry tradition, although for reasons, as you'll see later in my talk, I don't like using the human names to identify mathematical concepts, and I'll talk a little bit more about that later. Classical geometry is kind of what you think of when you think of the mathematics done by the Greeks. So before there was algebra, before anyone had ever written find X on a chalkboard somewhere, there was classical geometry, which, as we know, comes from the words G, meaning earth, and metria, meaning a measuring of. So geometry is measuring the land. It originated in surveying practices, as well as ways to analyze spatial relationships built on a particular set of axioms based on kind of some ground rules that we set aside as humans, and then decided to go from there and see where they took us. I like to see geometry as the first human attempt of speaking nature's language. Nature speaks to us through geometry, and we, a la like little children learning to read for the first time, babble back. I shared this quote with Renee, who I believe passed it along to all of you um, earlier today, but I'll just go ahead and put it up here for a second. This is Escher's regular division of the plane number 3. So Escher, who many of you have probably seen the work of, wrote very profoundly and beautifully on tessellations and the art that can be created using tessellations. Which can also be called tilings of a solid two-dimensional plane. And Escher makes the claim here in 1957 that the regular division of the plane had been considered theoretically to that time. And in fact, as you'll see later, it had been considered pretty comprehensively, not just of the plane, almost a century prior. But he points out that it's not exclusively a mathematical problem, right? In Escher's opinion, mathematicians, he believed, opened the gate to an extensive domain that comes from these plane tilings and divisions of the plane. But in his view, mathematicians are more interested in the way in which the gate is opened rather than the garden lying behind it. Escher speaks of the art that can be created using tessellations here. As an example of this, here is regular division of the plane 3. I don't necessarily agree with Escher. In fact, I would argue that to be a mathematician is not only to open a gate, but also to seek additional gates and potentially new gardens. So I'll see if we can make that metaphor a little bit more concrete as we go. But first, I'll put up some pretty pictures. So here are the Metamorphosis series of works by Escher. And so here, I'd like you all to take a look at each of these pictures just briefly and kind of take some time to let it impress upon you a little bit. See if we can come up with some observations. So the things that jump out at me as I look at these are some shapes. So I see some squares here. I see rhombuses here, as well as other diamonds. I see some hexagons here and here. I see some triangles over here. And then, of course, I see more natural organic shapes emerge from the canvas. So I see the lizards, I see the bees and the other insects, I see the fish. And then, of course, I see more man-made structures. So the labyrinths here and the chessboards and the buildings and the horses and in their armor. All right, so we've looked at these pictures. So I want us to go back to the things that we see recurring across all of these different motifs, which are the regular shapes. The average, everyday polygon. Oops. Skipped a slide. All right. So I'm going to go through really quickly and talk about what a tiling is. So a tiling, as you might imagine, is what you might do to your bathroom floor. You basically take a single plane figure known as a polygon, which is a non-self-intersecting plane figure made up of line segments like this wonky plus sign over here, this lightning bolt shape. And then you can see if you can tile a floor with that. There are infinitely many of those, right? You can kind of take any combination of lines as long as they don't intersect and come up with a polygon, as long as it closes up nicely. Now, we can also look at the smaller class of regular polygons, which are plane figures with equal edges and equal angle measures where two edges meet. So we've got this beautiful stop sign here, the regular octagon, or this pentagon here, which some of us think of as a house shape. But only 3 of these shapes appear in Escher's tessellations. They are, to give them their proper geometric names, the trigon, the triangle, the tetragon, the rectangle, quadrilateral, square, you might see it used differently in different contexts, and the hexagon. So these are the only shapes, if you were to go back and look at the Metamorphosis series, that you'll see appearing in Escher's work. Now, I wonder why that might be, and maybe if you're like me, that's a question you have as well. But here's a question for you all. How would you make a metamorphosis tiling? So this is the way that Escher went about it. And I like to leave this picture on the screen for just a couple moments. If we have any observations to share, feel free to jump in. What's going on here? Someone try to describe to me what this picture is illustrating in the metamorphosis art panel. What's going on here?
I think he's trying to leave empty spaces where protrusions, empty spaces in some places where protrusions from other spaces are going to fit into.
Absolutely. Okay. And where is he starting from? What is he taking from the empty spaces and adding to the protrusions with? He's using a base figure. In this case, he's using a hexagon. So he's using the solid shape of the hexagon in order to take what he has to add in to other places. And so you can follow these dotted lines to indicate kind of exactly where that addition and subtraction process is happening in reciprocity. But you can see that the original shape of this very characteristic looking lizard, which if you do live in Honolulu, you might have seen paneling a wall in Mo'iliili, happens to be just a little hexagon that happened to take on a little bit of a new life. This is a true metamorphosis process, is taking a single geometric figure that has no organic elements or even mannerisms to it and making an organic seeming shape from it. And if you'd like, you can try it yourself. You can take any triangle, quadrilateral, or hexagon. It doesn't have to be regular. You can just take a piece of paper and you can cut it up and then take whatever you cut off and then attach it in a different spot. And then you'll be able to make a tiling with that by tracing out the outline of your new shape. So that might be something for you to try. Now, why did I bring this up? Well, those three shapes that we brought up, right? The triangle, the quadrilateral, and the hexagon were significant to Escher. He found them really beautiful, and that's why he used them to inspire his art. They're pretty plain figures on the whole of it, that no pun intended. They're just straight lines and angles, but in a sense, Escher found them sacred. And so I'd like to pause, just don't have to answer it all, but thinking about what makes a thing sacred, right? Is it something that defies explanation? Is it the ability of its or the ability for it to recur in a pattern without seeming contrived? What kind of things do we categorize as sacred? Walt Whitman categorized the human form as sacred, if nothing else. So what do these things have in common? And here I'd like to talk a little bit about my experience as a dancer. So for me, I consider Bharatanatyam, and I'm really biased when I say this, one of the most sacred forms of dance, at least that I've practiced. And to me, if I were to speak on my experience of that, the reason for that is the geometry of it. The geometricity of Bharatanatyam is something that's undeniable to just about everyone who's watched it. And anyone who's spoken to me talks to me about how rigid the forms appear and yet how graceful, how there's simultaneously this juxtaposition between the sharp and the smooth and the curvy and the straight. So this idea of being able to describe exactly what makes Bharatanatyam so geometric doesn't seem to align with what makes it sacred. But at the same time, for me as a practitioner of it, knowing why I can do a certain step correctly connects me deeper to it on a sacred level, on a spiritual level, I should say. So I'd like to pause here and just offer you all the chance to share. Is there anything that makes something sacred to you? How do you define sacredness? And we'll see if we can address that. That's okay. If we're not feeling like sharing now, maybe we can come back to it later. I know there's time for us to talk. So now we get into the math. So I hope you'll bear with me here. Another more significant aspect of the idea of sacred human geometry as it appeared in Theosophical Society and in its predecessors in the Pythagoreans and in the classical geometers is the fact that there are exactly 5 regular polyhedra. This kind of defies our understanding of geometry a little bit because our intuition tells us, well, if there are infinitely many regular polygons, remember those are the two-dimensional versions, there should be just as many equivalent three-dimensional shapes. But the 5 regular polyhedra are the only possible equivalents, meaning where we've got the same number of faces meeting at each vertex as there are regular polygons. As there are edges in regular polygons. But you'll notice that in this case, there are only 3 regular polygons that are being used, which seems to limit the number of polyhedra that can be formed. Why is that? Well, we'll see in just a minute, but I want to call your attention to the fact that these polyhedra all have identical faces. So around each vertex, you'll see 3 or more individual polyhedra or polygons, two-dimensional shapes. And in this case, they are the triangle, the quadrilateral, and the pentagon. Why those 3 shapes? Well, we'll get into that in just a second. But I'd like to introduce you to these guys, which if you've ever played Dungeons and Dragons, you might know as your dice set. You've got your tetrahedron, you've got your hexahedron, also known as a cube, you've got your octahedron, you've got your icosahedron, and you've got your dodecahedron. So these are our kind of quintessential set of platonic solids that have equally weighted faces. And again, they are comprised of 3 shapes: the triangle, the square, and the pentagon. Why just these 3? And here, I'd like to think a little bit more about what we consider sacred. So sometimes to defy explanation is a description that I've often seen given to the sacred, is something that touches something within us without us exactly knowing why. And to some extent, it's like removing the magic of Christmas by telling someone that Santa Claus isn't real, right? Do we even really want to know? Do we want to know that? Do we want to have that mysticism removed from the incredible statement, the incredible truth that there are only 5 of these? Does that somehow remove some of the sacredness? And to that effect, I'd like to present the possibility that its explicability is exactly what makes it so inexplicably beautiful. So this is my warning to all those of you who are like, math's not my thing. There's going to be some math on the next slide, but we'll hold each other's hands and get through it together. So it should be okay. So why are there only 5? So we have a few rules that we laid down. Remember, we said we had to have the same number of faces, at least 3, right? Because otherwise it wouldn't be 3-dimensional. It would only be 2-dimensional. Have to meet at every vertex. The same number of faces that have to be the same. So those faces all have to be identical. So for instance, here we've got 3 different squares that are identical meeting at a single vertex. I can kind of flop that around. If you can imagine sticking 3 pieces of paper together at a corner and putting a pin in that, you can kind of move them around. You can kind of wiggle them. But in some configurations, it takes on a more 3D structure. And at that structure, we can start to decide how many angles are actually fitting around that individual vertex. So here, if this is a square, then this angle we know is 90 degrees. So around this angle, each of these A values measures 90 degrees. So we add that. That means there's a total of how many degrees? Does anyone want to feel brave and calculate some numbers for us?
What, 270?
That's it. 3 times 90 is 270. Excellent. So what we notice is that if we have 3 squares around a single vertex, we run into 270 interior angle sum. That's what we call that. But we know that if we added 1 more square, we'd have 270 plus 90, which is 360. And if we knew that we had 360 degrees around a single point, the solid can no longer be a solid. It sort of squishes flat, as you can see here. So that interior angle sum for this to be a solid has to be less than 360 degrees. So no matter what platonic solids we try to construct, no matter what regular polyhedra we come up with, the solid has to have interior angle sum less than 360 degrees. So what are the chances that we can get those to come up? Well, thankfully, I did the math for you, and I put all my numbers into this pretty little table over here. So if we can look through this, you can see that I've tried to sort this by, first of all, which polygon I started with, right? Because I can only make exact copies of those polygons around each vertex, right? So I started with my triangle, and I said, okay, let me put 3 triangles around a vertex, because I have to have at least 3. And each triangle, equilateral triangles, have interior angles of 60 degrees. So if there are 3 triangles around a single vertex, I've got 3 triangles times 60 interior angles. That gives me 3 times 60, 180 degrees per vertex. That's definitely less than 360, so we're good. That's a tetrahedron. That's the solid that we get when we put 3 triangles around a single vertex. And I can go back to the slide that shows us exactly what that looks like. So around this vertex, there's 3 triangles, and each vertex is identical to that. There are exactly 3 triangles around every single vertex. So we go back to our table. We start looking at our numbers. We start seeing, okay, so some of these, we can get 3 different platonic solids with angle measures less than 360 degrees formed out of triangles. They are the tetrahedron, the octahedron, and the icosahedron. But when we get to 360 degrees, that's when we have 6 triangles around a single vertex. We know that it's exactly 360. And so instead of it being a solid that we can close up into a nice shape, it becomes flat. It becomes part of a piece of paper. And that's when we create a tilate. When you can have enough shapes to put together around a single point and get exactly 360 degrees, you can tile your bathroom floor with that thing. You can make a tessellation out of that thing. And Escher probably did, knowing him. So we can look through these shapes and we can start doing the multiplication for ourselves. And we can see, yep, we got that cube that Cliff calculated for us earlier at the 270 degrees, 3 squares around each vertex. That gives us our cube. When we get to 4, we got our tiling, we got our checkerboard pattern. 5-sided figures, pentagons, if you put 3 of them around a vertex, each interior angle there is 108 degrees. You don't have to measure that yourself, just take my word for it. You multiply that out, you get 324, and that's just barely a solid. And if you look at the icosahedron, which is the platonic solid composed of pentagons, you'll notice that it's kind of really round, just like the dodecahedron. So, where it does start to get a little bit hairy is when we get into the hexagon, where we try to put 3 hexagons around a single vertex, but because each hexagon has an interior angle of 120 degrees, we already get 360. We get a flat shape. And so we get no solids from a hexagon. And hope you don't mind, I didn't even try for 7 because I knew if a hexagon was too big, it wasn't going to work. So what do we notice here? We notice we got exactly 5 possible solids, right? But then the other thing that I didn't mention is that we got 3 shapes that tiled. We got the triangle, the quadrilateral, and the hexagon. If you remember, those are the exact 3 shapes that Escher used for his tessellations. So there was mathematical reason to why there are 5 platonic solids and no more, and why Escher used only 3 two-dimensional figures in his tessellations. Here's a picture for those of us who prefer drawings. So you can see if I've got room to fold this up, then I can make a solid out of it. So this is me putting 3 equilateral triangles around a vertex, 4, 5, and then 6. So 6 gives me a flat hexagon. And I know I can tile the plane with that. I know I can tile my bathroom floor with that. So I don't even have to bother with 7 and higher. Any questions about that? Any comments we want to share about this process? How was it for us? Do we feel comfortable with that?
Yeah,
Was
that
it a
was
little
good.
painful to see the numbers? Felt good? Okay, I'm glad. I know sometimes the numbers can be a little traumatizing, so I don't want to throw too much at us, but as long as we're okay with that. Okay, so now we get into the invisible gardens I was talking about. We started with polygons. Now, I want to add in a little bit of linguistic fun facts here because the languages that we speak tell us the most about ourselves. Polygons comes from gonu, the Greek word for knee. So the word gon in polygon comes from knee because the knee bends a very specific way. It can't bend in 3 dimensions like the rest of us, or several of our other joints can. It's a 2-dimensional range of motion. Now, if we think about the polyhedron, remember those are the 3-dimensional versions, also called solids. Give them the name platonic solid, but I don't like doing that because it leaves out a lot of the credit. But we go back to the polyhedron, right? The polyhedron, hedron comes from the word for face, which, as you can see, can turn in all 3 dimensions. So we go from the knee to the face, and we're using these terms that tie us very intimately to our own bodies because this is the geometry that we know and love. This is the sacredness of our own geometry, of our human geometry. But then we start to leave 3 dimensions. We ask ourselves the question, well, if we can put a certain number of line segments around a point in 2 dimensions, we can take a certain number of shapes in 2 dimensions and put them together in 3 and sort of move them around and see if I can make a solid out of them. Why can't I do the same to 3 cubes? Why can't I put 3 cubes around an object and say, what kind of a figure could I make if I put the same number around every vertex? Well, the answer is because we are limited to our palace of riches in 3 dimensions. So at some point, we no longer have that beautiful visual intuition that tells us, oh, there's got to be a pattern here. And so at that point, we rely on mathematics. And thankfully, in 1857, exactly 100 years before Escher made his statement about the gardens and the gates, we had some mathematicians led by James Coxeter, who discovered that there are exactly not 3, not 4, not 5, but 6 regular polyhedron equivalents in 4 dimensions. We call those 4-dimensional polytopes. 6. It seems super random, but I promise you it's true. No intuition there, but it's true. Now, if we were to go higher, okay, maybe more dimensions gives us more leverage, right? Maybe we can make more than 6 in 5 dimensions, but it turns out 5 dimensions and higher, we get 3. And that's so unsatisfying. It feels very whatever the opposite of sacred is, but it's true. And I don't know how you feel about that, but it's kind of upsetting emotionally while it's also satisfying mathematically. So I don't know. That's just where math takes us, right? We ended up in a garden that we weren't really sure we wanted to be in. But here's the thing about that. I say that you have to trust me on this, but it isn't really something that you have to trust me on because proof doesn't lie. Proof is essentially our own sanity checker against the patterns that we would love to see and believe, the false prophets of patterns that pop up here and there in the idea of learning the sacred in the course of our lives. So I'd just like to leave you with a few parting thoughts. The first of those is the fact that those patterns bothered me, right? And I'm sure they bothered some of you as well. So why is it that we feel patterns before we know them? Why do we have to have that sense of satisfaction about something? And if we don't have that satisfaction about something, does that mean it's something we should avoid? Like if we understand something, but we still aren't happy about it, like, is that something that we shouldn't have tried to understand? What's our intuition doing there? Is it guiding us towards a right answer, or is it misleading us? Is it telling us, no, the answer's over here, when really that's going to not work to tile our bathroom floors? And finally, this is what I think comes down to the end of my point here. I came in here knowing most of you from my perspective as a dancer, right? But I wanted to share this facet of myself with you as well, because being a mathematician is just as intimately a part of my identity. And I think that the 2 sides of me really inform each other a lot more than I tend to give both of them credit for. But the idea that mathematics and dance have this one thing in common, that they exist outside of humanity. And yet they are 2 of the most human things that have ever been done. Humans naturally dance because nature dances. Humans naturally do mathematics because mathematics is the language of nature. Nature communicates to us through patterns, patterns in movement, patterns in numbers. No matter what it is, that's how we have flourished for this long. But Does that make nature sacred? Does that make something beyond us sacred? Is that the definition of sacredness? And so you might be looking at me and being like, duh, that's exactly what sacredness is, right? Like, why didn't you just say that before when I was asking? So that's not what I'm saying. I'm saying if something were not to be perceived by a human, would we still consider it sacred, right? Are these polytopes still sacred if we didn't live in 3 dimensions? And why is that the limit of our imaginations? Why is that the limit of our intuition? And is sacredness really just what cannot be understood by us? Or is it exactly that which we can seek explanation for and maybe fall short some of the time? Anyway, that's all I had to say. Thank you all. And I'd love to hear the discussion that ensues. I really appreciate your time. Hopefully I didn't go too far over.
No, no. Wonderful. Thank you, Janani. Okay. Woo! We're glad here to have someone else here who immediately raised their hand in terms of feeling comfortable with math, comfortable enough to spend their life doing it, as Janani has. Whether in motion or whether more in a still setting, one would think doing her more rigorous mathematical mental part. Could you, without going too deeply into it, just give a little bit more of an intimation of what a polytope is in terms of this idea of multiple dimensions? Or is that just going to get us too far afield?
I can try to give like the best intuition I have, which is can I draw a picture actually?
Yeah.
Okay. I'm it says I can't whiteboard, but let me see if there's a way for me to do this. Okay. Oh, I don't know what just happened. Sorry about that. Do you know if you can enable participant whiteboarding? Is that a thing that you can do? Sorry, I think that might just be the easiest way to do this, unless I were to.
Yes, I don't have that
Okay.
knowledge or skill. But you could
Okay.
draw it on a paper and hold it up to be
I
really
I
low.
I think I'd prefer this. Okay, so I want to go back to just a new tab here, because then I can open a new slide and just have it be blank for us. All right. So, right. Sorry about that. My chalkboard is probably the best thing I could do a mathematical picture on. Mathematicians are known for being really sort of punctilious about their chalk. So we often spend like most of the department's budget goes towards buying like really nice chalk from Korea. Um, yeah, no, I really don't know if I can draw
Okay,
this. Maybe I'll
that's
get
it.
a piece of paper. I don't know if anyone else wants to share anything in the meantime. I'm gonna go get a piece of paper and draw this.
Okay. John, did you have something that you could maybe start the rest of us on? I saw your
Oh,
hand.
yeah. Well, actually, I wanted to find out whether M.C. Escher came to his discovery of the 3 forms that he could use for tiling through a study of geometry, or did he come to his tessellations through a study of geometry? In other words, was he an artist first, or was he a mathematician second, or vice versa?
Sorry. I would argue that we're all mathematicians first, just as I would argue as we're all artists. And Escher was pretty much the same way. So I would say that so Escher, as a student of mathematics, was really fascinated by geometry. It wasn't by any means his like profession or anything. I actually don't know what Escher did, but he studied it in school like we all had to. And from there he took his geometric impressions with him. There's a great book called Gödel, Escher, Bach that really fully explores the interplay between mathematics and art and music even. So there's more detail in that. I don't know if any of you have read it, but
Haven't, but thank you very much, Janani.
Okay.
I don't want to answer Renee's question when she's walked away, but
She's right here.
oh, sorry. Okay. I was just going to start with the zero dimension. So the zero dimension is what we call a point, right? And if we have a point, what we can do is we can put infinitely many of them close to each other along a single direction of travel, along a single dimension of movement, and we call that a line. We've created a one-dimensional figure. And then we can take infinitely many of those lines, those infinite one-dimensional figures, and we can make what we know of as a square. Excuse me while I color. Yeah, infinite number of lines, same width as the line. Then we can take this square and we can do what this sticky note pad has already helpfully done for me, which is sort of make infinite copies of the square and stack them one behind the other to make, if I had a whole bunch of sticky notes, to make a cube. Agreed? So to extend our imagination into higher dimensions, we take the cube that we were able to make, we duplicate the cube in some direction, unbeknownst to us, because, again, we only have the 3 dimensions to play with, right? We have the idea of length, width, and depth, or height. So we've got another dimension somewhere, and we duplicate that cube in that as many times as the width of the cube allows. So that, whatever that would be, is the 4th dimensional analog of a square, which is called tetratope for four-sided polytope, four-faced polytope. But the name that mathematicians have given to it is a tesseract. The other way you can think about it is, like, you know how people draw a cube by drawing 2 squares and connecting the vertices? So it looks like that. If I were to draw another cube in the same way, then I would just have to draw squares connecting each vertex of this cube to this cube. And if that sounds kind of trippy / impossible to visualize,
Hold it closer. Okay.
I can't draw squares connecting 2-dimensional or 1-dimensional vertices to 2-dimensional edges, or to 1-dimensional edges to 2-dimensional faces to 3-dimensional cubes. But if I were able to do that, then that's what you would visualize. You would visualize squares connecting each of these cubes to each other. There's a way to visualize it. I think there's like an animated GIF on Wikipedia that does it well, so I can just put that in the chat if you want to see what that would look like. If it helps, I will say this. There was an incredible book called Flatland, written by someone who went under the pseudonym A Square. His name was Edwin Abbott, and he wrote in like the 1700s. It's an excellent book. Highly recommend it to anyone like on Earth, because I probably wouldn't be doing mathematics without it. But the interesting thing about it is that it comes from the perspective of someone who's critiquing like political structure in back then England, which definitely deserved a lot of critique if you want my opinion on it. But more so, it's got like this incredible explanation, elucidation really, of how you can visualize higher dimensions. And in that, he makes the claim that the 4th dimension, right, that dimension that we can't describe because we only have the 3 that we know about, is inside. Because if you can think about it, all of the new dimensions are just a way of seeing inside the previous dimensional shape. So if you think about it, we can see the inside of that square, and that's how we know, oh, we can duplicate it by stacking copies one on top of the other. So the idea is we should be able to somehow go inside a cube and then visualize the creation of a tesseract by duplicating the cube inside it some number of times.
Wow. John.
Yeah, I have another question. Some years ago, I attended a meeting at the Institute of World Culture in Santa Barbara, and they had invited this professor who was visiting at, I think it was an Institute of Theoretical Physics or something at UC Santa Barbara. His name Roger Penrose, who later won a Nobel Prize in Physics for some very interesting work he did. And the talk was on Penrose tiles. And to my best recollection, which I really did not understand, and we were all expected to bring an interesting question to ask Roger Penrose. But anyway, he was explaining this Penrose tiling as it's like an infinite series of patterns that don't repeat themselves. So they're tilings, but they're non-repetitive. So can you explain that at all, what that's all about?
I can try. First of all, that's wicked cool that you met Roger Penrose. That's like celebrity status. But I don't know if anyone else wanted to take a shot at it first. No? Okay. So a Penrose tiling is different from a tiling like I was talking about before. So the Escher tilings or the tessellations are called that because they are repeating, right? So you take a shape and then you repeat it a certain number of times. Whereas a Penrose tiling is specifically about not repeating. So that sort of seems like, why would you want that? But there's reasons why it's significant in physics, and that's why he got the Nobel Prize for it. There's actually like a lot of interest in specifically these areas of what seem like just trivial geometry, but are super applicable to different areas. But that's not the point. To explain what a Penrose tiling is I would have to point to this discovery that was made like less than, I think, 2 years ago, where they invented a new shape for the sake of completing what's called an Einstein problem, which is a Penrose tiling, a tiling that never repeats anywhere across the board, with a single shape. It was a 13-sided shape and it was wacky, and they called it the hat. So it's really interesting. If you can think about a Penrose tiling as you want to tile your bathroom floor, but you don't want any part of the bathroom floor to look exactly like any other part. So if I were to take like a little tiny picture of one part of my bathroom floor, I was like, okay, there's only one place on my bathroom floor that this picture could be from. Make sense? So if you've got a picture, you know exactly where on your bathroom floor that spot is, because that's the only spot it appears. Now, the idea, what makes a Penrose tiling so cool is picture this issue where you've got like one spot on your bathroom floor and you know exactly where it is, and then you can do the same thing for every other spot on your bathroom floor, except your bathroom is infinite. So you're using an infinite floor to kind of tile and not repeat that pattern anywhere. And it's like fascinating. Someone has actually sent me my partner who's in my house is listening to me talk. My partner's in physics. And so he just sent me a simulator that I could share with you all. So thank you, Tom. And I'm going to put it in the chat if you are interested in simulating Penrose tiling for your own personal interest.
Great. Thank you very much. I'm going to get started on my bathroom right away.
Yeah. Good luck with that. Send us a picture when you're done.
Carolyn. Oh, could you turn on your mic?
This is all beyond me, and I just watched the better part of an hour also on polygons and all. But the kind of structures you were presenting us with, if we understood them and we were an architect, could we say, okay, I want a beautiful house, or I want a really sturdy house that will last 100 years? Would this knowledge, a real facility with what you've been talking about in polygons, would it be helpful in those goals as an architect?
Just to clarify, you're saying if I were an architect,
Yeah,
would it help me to have a knowledge of these polyhedra and things like that?
yeah,
That's
the
fair.
three you were working with.
Oh yeah. That's a great question. It actually is like the perfect question. So I don't know if it's beyond you or you're beyond it. So let me explain what I mean by that. We started talking about sacred human geometry, right? And sacred human geometry is like a term, as far as I know, I'm very like new to all of this philosophy behind it, but the idea is that there's things that cultures across the world consider sacred for XYZ reasons, right? Why are those things sort of universal? And if so, is there something sacred about that universality? Is that what makes something sacred? Is that everyone can recognize what a triangle is, right? And where it appears as significant to us culturally. And so to answer your question, the reason is exactly because these shapes are so structurally sound. So the triangle, incredibly strong shape, right? That's why the pyramids are still standing. Rectangles, there's a reason we build our houses out of them because A, they're very space efficient. They're more space efficient than triangles, which is why even though, triangles are very structurally sound, I mean, I'm not the person to speak on this. We have someone who is like a doyen in the field of construction. But, like we have that idea of a rectangle has certain perks, which is that it is very good at saving space. So you can pack a lot of things into different corners of it without having to worry about, I'm not using all my vertical space or something like that. Where a triangle, you only have this much vertical space to kind of work with. You have that upper corner of it. Does that kind of make sense? So it's understanding not only the mathematical properties, but also kind of the qualitative properties of each shape that could assist someone whose field is not just like technical, but also kind of artistic in the way that an architect's is.
Mhm. Okay.
And we also know that if we were an architect for bumblebees, the hexagon would be very, very, very special.
Absolutely. Yeah, I should not have left the hexagon out. Hexagons are the bestigons, as they say.
Cliff.
I think it's Plato who said that God geometrizes, but one of your points is that behind nature or through nature, there's geometry there where everyone looks at nature. And of course, we're part of nature. But I was wondering, you were talking about the Penrose thing that doesn't repeat. What about pi? How does pi fit into all this? Because I saw that one picture of the lizard that Escher drew. Looked like there was a bunch of circles involved. And of course, pi has so much to do with circles, and it's non-repeating. Is it some kind of important key to understanding the geometry of nature?
Does anyone have any thoughts on this? Because I'll jump in with an answer. I just don't want to be answering questions. There are other people with answers. Here's how I interpreted your question, which is you see non-repeating patterns in Penrose tilings, which are, as I've mentioned, significant for physics and all sorts of different cool things. And you see non-repeating patterns in pi, right? So you've just identified a meta pattern. Do you see what I'm saying? You've identified the pattern that this is non-repeating and this is non-repeating. So you've identified the pattern that this doesn't have a pattern and this doesn't have a pattern. So what you've identified there is a really significant idea. It's irregularity, right? It's the absence of a pattern. And that's just as important in mathematics. Just like we talked about the pattern that didn't quite work out, right? Where we had infinite numbers of regular polygons and only 5 regular polyhedra, and then 6 4-dimensional versions and then 3, 5 dimensions and up, right? That's an example of an irregularity that mathematicians love. Is it interesting beyond noting that it's an irregularity? I would say probably not. But if you were a mathematician, would that be enough to get you a dissertation? Maybe. Not necessarily that specific observation, because you're right? But irregularities is what research mathematics is all about. It's about knowing when certain observations apply to the entire bevy of what's in front of you versus a small set of it. And identifying that set of properties is actually a large part of what research mathematics does today. I'm trying to think about you asked like really interesting, like the way you phrased it or the way you brought up that question, you had something else in there that I want to address. So you said something about pi, and what did you say before pi? Or like, oh, you talked about the circles in the Escher picture, right?
Yeah.
So that's really significant, right? Why is it circles that appear there? Because I kind of lied to you a little bit. So I told you we were talking about polygons, right? But if you remember, what I was saying is that the polygons, when you put them around a vertex, can't be 360 degrees, because if it was 360 degrees, it would be flat, it would be on a piece of paper, and then Escher would have made a thing out of it, right? That's the point, is because if you can make a circle, then you get 360 degrees on a piece of paper. And so all of those tilings are comprised of circles. So if you can draw a circle around several different polygons around a single vertex, that's another way to know in which that you can tessellate. And the only 3 shapes where you can draw a circle around a single vertex with several of them like drawn around it is if you have a triangle, square, and a hexagon. You can also do them with sort of combinations of triangles, squares, and hexagons. So you can use a like a diamond and a square to make a different kind of tiling. You can use a triangle and a square to make a kind of pentagon, but not a regular pentagon that will tile. I can draw pictures for this, but like circles are deeply involved in all of it. But pi's nature as an irrational number is less tied to it, I would say.
Okay. I'm wondering, speaking on the sacred, and I need somebody, by the way, to track our time because I can't see it on this particular computer. So maybe
3:56 Hawaiian time.
Okay, thank you. If anyone has a sense of the sacred in motion, so that's a question that I posed to Janani to start us off on the conversation the two of us had before we had this meeting. Does anybody have a sense of the sacred in motion? Since we are speaking from within the context of still and moving center.
Yeah, a crowded city street with a lot of people walking.
Yeah.
Yeah, I think that's a very good question you asked, Renee, but I wouldn't know how to answer it. Because it's really about, I don't know, the use of energy and form or structure that constitutes life.
Mm-hmm.
That people are, that we're living, but directed beings, I think, something like that. That we have this energy, but also there's in a sense, there's an invisible set of boundaries within this whole field where energy is busy. That is what makes it possible to give intelligence direction to the use of all that energy. And it constitutes life. Life is both structure and energy.
Mhm, mhm. Anyone else? Bob?
Thank you. It was very interesting. And I was thinking as you were talking of how I would look at mathematics in the sense of um, certainty and truth and intuition. So that at a certain point, to answer your question about motion or life, as Carolyn says, it depends upon your dimension. In flatland, if a line comes at you sideways, it's a line. You can see it. But if it comes at you perpendicular, it's a point. So it'll skew you. You can't see a point. It's one pointed. And so they always have to scream to let you know that they're coming. Um, and all the other shapes will come as lines. It doesn't matter if it's a square or five figure, whatever number of figured it is. Spinoza actually talked about math doing 1,000 figured uh, shape. And he said, well, you can do it mathematically. There's certainty involved with it, but you can't imagine it. And Plato in his cave talked about, well, what would happen if somebody did a cave movement in flatland? In other words, rose above the plane, looked down and went, oh, wow, there's circles, there's squares, which they cannot imagine at their dimension. If he came back and tried to explain it, they would burn him at the stake. He's a heretic. And similarly, Plato was saying that in terms of our world, our three-dimensional world is limited if our intuition takes us to a higher truth. That is light and infinity. So there's a certain sense where geometry is of a perspective, but then what happens when you move across our imagination into non-Euclidean geometry? In other words, if you have a topaz figure that wraps around itself, you can do geometry on that. You can do geometry on a sphere, and it's different. You can have three right angles in a triangle on a sphere, but obviously not three-dimensionally. And so you're sort of working with all of these elements, and I'm wondering, as the sacred comes in, whether it's how you interpret that. A square, as you say, is a wonderful figure. The American Indians thought it was just stupid, all those squares and shape. They just felt, you're so square minded. Everything has to be 90-degree. Circle, a hoop, is a living figure. Now, you could probably say that a square or a triangle were sacred figures too, but certainly how you develop that leads you, in a sense, to your truth. And so I was just wondering how all of that kind of works. It's kind of goes beyond the mathematics into how you interpret the mathematics, both in terms of certainty, but also in terms of truth. Um, and it's interesting as you get into irrational, as was said earlier with pi. Once you're an irrational thing, you're really dealing with dimensionality that is non geometrical. I mean, it literally can't be put into a shape if it's irrational. And the Pythagoreans saw one of their great mysteries with the Pythagorean theorem, which did have an element of the square root of 2, which is also irrational. So they actually saw that as a heresy if people tried to question their mathematics through something that they saw was, I don't know, it led them away from the mystery of mathematics into the mystery of non-mathematics and how they dealt with that, because it was still philosophy. It was still trying to make sense out of the world. Um, so they had problems with the irrational, since Pythagoras was Euclidean. Anyway, it just seemed interesting how all those things work. Certainty is an interesting dimension, but it's one dimension. And philosophers like Spinoza, Wittgenstein tried to do a geometrical thing of certain steps each way through their philosophy. But at one point, I don't know, they're kind of intuitionally open whether there are mathematical certainties beyond that. And I think they're sort of dealing with the mysticism as well as the certainty.
Hmm. Thank you. Bob, I'm wondering if you should have raised your hand too when it came to people comfortable with math. We're going to call
Well,
on
I'm very
John.
comfortable with math, but the second part of your question is whether you'd want to spend the rest of your life doing it. And I was a math minor way back in the day, but I haven't touched math for 50 years. So I can't say I'd spend the rest of my life doing it, but I love it.
I'm realizing just intuitively without being able to see a clock that we're probably over the hour. So I want to call on John, and maybe you can round us out, John. Maybe you have a closing remark that you can make.
I do. It's a very short one, though.
Yeah.
So I just wanted to read this. When you asked the question about motion of the sacred, what can we conceive of that moves that we would call the sacred? Anyway, Professor Raghavan Iyer made this very pithy comment. He said, "Man is God, moving as nature. And when man realizes God as himself, he is the master of nature, and it makes all three sacred."
Oh, thank you so much. Our conversation last week was on the German mystic Catholic Meister Eckhart, who was helping us to see the identity of ourselves with the divine, which is absolutely everywhere. So that was a really perfect connection to bring to us, John. Thank you so much. I really want to thank Janani for being willing to speak to us that might or might not have had very much of a comprehension of mathematics, and being someone who has a very deep comprehension to be willing to make some translations for us, which is really important to be able to do, to bridge some gaps and allow us to awaken the mind a bit more and stretch it in new dimensions. And it's been said that a mind once stretched in a new dimension may never shrink again, and that's a good thing. So thank you ever so much. I'm going to ask Mary if she can tell us the, because, yeah, and I will call on you, Chinani, I see. Mary, could you tell us our theme for next week since you have an almanac?
Okay, next week's theme is involution and evolution.
Okay. John, are you here for involution and evolution? Is that you?
I'm here for half of it.
Okay, great. Next week we have both John Powers and Elton Hall, both wonderful thinkers, philosophers, who are going to be speaking from the theosophical tradition on these ideas of involution and evolution, and plan on being here for an extra 15 minutes so that we can make sure we can hear from both of them and still have conversation time.
Okay.
Yeah, Janani.
I just wanted to say maybe one more connection that I wanted to make that was just sparked by something you said was math and dance have taught me a lot of the same lessons. And the prime one is humility. Math is one of those things that really just teaches you that when you think you understand something or you see that glimmer of, ooh, I think there's something there, you often have a lot farther to walk to get to it. And I would say that just because the glimmer is farther away than you think doesn't mean you should be discouraged by the distance to walk. And that's something that math has taught me. So I think, yeah, that's what I have to say.
Janani, I would say that anyone that's striving to get a PhD in math is not just humble, but brave. As well as Bharatanatyam, you have to be brave to get on a stage and do that amazing dance form. So you exhibit not just humility, but a lot of bravery.
Yes, indeed. Thank you ever so much, Janani, and everyone who joined us today, including Rainbow and Adela and everyone who spoke up. It's always good to have listeners as well as those who speak. So thank you all so much. Special thanks to Janani, and we'll see John again next week. Aloha all.
Mahalo, Janani.
Thank you,
Okay.
Janani.
Thank
That
you,
was wonderful.
Janani. Wonderful.
Aloha.
Yeah.
Mahalo.
Mahalo.